This is the F-35, arguably one of the most advanced fighter jets, and right now, it's about to do something only one fighter jet on Earth can do. A pilot pushes the throttle forward. 43,000 pounds of thrust slam into the back of this airframe. The jet accelerates down 600 feet of flight deck, no catapult, no launch system, just raw engine power and a short stretch of ship. The nose lifts, the gear clears the edge, a stealth fighter airborne. But what makes this aircraft different from every other fighter isn't the takeoff. It's what happens when it comes back, and the engineering required to make that happen is, honestly, borderline insane. The engine pushing this jet through the sky is the Pratt Whitney F135, the most powerful fighter jet engine ever produced. 43,000 pounds of thrust in full afterburner, enough to push 25 tons of aircraft past Mach 1.6. It can even sustain Mach 1.2 for 150 miles without afterburner, a capability called Super Cruise that was once exclusive to the F-22 Raptor. At 30,000 feet and 900 miles per hour cruise speed, this jet is functionally invisible. The F-35's radar cross-section, the electromagnetic signal it bounces back to enemy radar, is estimated to be roughly the size of a golf ball. A conventional fighter like the F-16, the size of a car. That difference determines whether an enemy missile locks on at 200 miles or 20. On the airframe, you can see why. Every access panel has serrated edges that scatter radar waves. The surface is coated in radar-absorbing material. Think of it like shining a flashlight at two different surfaces. Aim it at a mirror and the light bounces straight back. Bright, obvious, impossible to miss. That's what radar does when it hits a conventional fighter. The signal bounces right back to the radar station and the aircraft lights up like a Christmas tree. Now aim that same flashlight at a matte black wall. The light scatters. Most of it gets absorbed. Almost nothing comes back. And that's what the F-35 stealth is doing. Additionally, weapons are carried internally, hidden in two bays that only open when it's time to use them. Even the engine intakes tell a stealth story. Earlier fighters like the F-16 used a gap between the inlet and fuselage to divert slow-moving boundary layer air. Air that builds up along the aircraft's skin that can damage engine turbines if it gets inside. Each rotation, the turbine blade passes through slow boundary air on one side and fast free stream air on the other. That cyclical bending is a recipe for fatigue failure. The F-16 solution was a boundary layer diverter, a gap that works aerodynamically but creates a radar reflector. The F-35 replaced all of that with a diverterless supersonic inlet, that seemingly simple bump on either side of the fuselage you see here. It looks like nothing, but it performs three functions simultaneously. It creates a compression zone that pushes turbulent air away from the engine, scatters incoming radar waves, and lowers drag. One bump, three engineering problems solved. It also reduced weight by 30% compared to a conventional inlet system and lowered both production and maintenance costs. This is what fifth-generation engineering looks like. Every surface, every curve, every bump is doing multiple jobs at once. Now look inside the cockpit, because what the pilot sees from inside this aircraft is unlike anything in any other fighter jet. Each F-35 pilot wears a custom-molded Generation 3 helmet-mounted display system that costs roughly $400,000. It replaces the traditional heads-up display entirely. Every piece of flight data, targeting information, and sensor imagery is projected directly onto the visor like a VR headset. No more looking down at instruments. Everything is on the glass in front of your eyes. But here's the genuinely mind-bending part. 6 high-resolution infrared cameras are mounted around the outside of the airframe. They provide full 160-degree spherical coverage and feed directly into the helmet. When the pilot looks down through the floor of the cockpit, they see the ground below them through the aircraft. Look behind, you see what's behind you. This system has tracked ballistic missiles at ranges exceeding 800 miles. It tracks everything simultaneously, without the pilot pointing or aiming at anything. The F-35 also carries an electronic warfare suite with 10 radio frequency antennas embedded in the wings and tail edges. It detects hostile radar from every direction, geolocates the threat, and can jam enemy systems. The aircraft knows who's looking at it, from where, and with what, before the enemy even knows the F-35 is there. And then multiply that by an entire flight. F-35s share sensor data in real time through a secure data link called Link 16 without breaking radio silence. Every aircraft in a formation sees what every other aircraft sees. One jet detects a target, and every jet in the formation instantly has that targeting data. The pilot who fires the missile might not even be the one who found the target. The flight operates as a single networked entity, a hive mind. So you've got a jet that's invisible to radar, sees in every direction, jams enemy systems, and shares everything it knows with every friendly unit nearby. It first saw combat in 2018 with the Israeli Air Force. Since then, it's been used by the United States in operations across the Middle East and by the UK in Iraq and Syria. Over 1,300 have been delivered to more than 17 nations, from the UK and Australia to Japan, South Korea, and Norway. The US alone plans to buy 2,456 through 2044. Making it the backbone of American tactical aviation for the next 5 decades. The aircraft is expected to remain in service until 2070. Pilots who haven't been born yet will fly this aircraft. But none of that is what makes the F-35B special. Everything I've just described, the stealth, the sensors, the hive mind, all 3 variants of the F-35 can do that. What makes the F-35B unique is something far more difficult, and it starts with a problem that goes back decades. The U.S. Navy operates 11 supercarriers, massive nuclear-powered floating air bases with catapults that hurl aircraft from 0 to 170 miles per hour in under 3 seconds. The Marines don't get those. The Marines operate from amphibious assault ships, vessels like the America-class LHAs. These ships displace about 45,000 tons. They're big, but their flight decks are short. No catapults, no arresting wires. If your aircraft can't take off in under 600 feet and land vertically, it doesn't fly from these ships, period. For 30 years, the Marines flew the AV-8B Harrier II. It could take off short and land vertically, which checked the basic boxes. But the Harrier was slow, limited range, modest weapons load, and absolutely zero stealth capability. In an era of advanced surface-to-air missile systems like Russia's S-400, sending a non-stealth aircraft into contested airspace is essentially a one-way ticket. The Marines needed something radically better. Picture a Harrier approaching a modern battlefield. No radar-absorbing coating, no internal weapons bays. Every surface broadcasting its position to every S-400 battery within 250 miles. The pilot knows he's visible, he knows the math, and he knows the Marines deserve better. In the 1990s, the Department of Defense launched the most ambitious fighter program in history, the Joint Strike Fighter. The plan was audacious: build one aircraft in 3 variants for the Air Force, Navy, and Marines simultaneously. One airframe to replace the F-16, the FA-18 Hornet, the AV-8B Harrier, and eventually the A-10 Warthog. The F-35A for conventional runways, the F-35C for carrier catapults, and the F-35B, the variant that had to do what no stealth aircraft had ever done: take off short and land vertically on a moving ship. 2 companies competed, Boeing with the X-32, Lockheed Martin with the X-35. In October 2001, Lockheed won. The deciding factor? Their short takeoff and vertical landing, or STOVL, design actually worked. The X-35B demonstrated a stable hover, vertical landing, and short takeoff in under 500 feet. Boeing's direct lift approach couldn't match it. The concept was pioneered by engineer Paul Bevilacqua at Lockheed Martin's Skunk Works, and it traced back to classified research from the 1980s. But here's the engineering challenge that made this nearly impossible. How do you fit a vertical landing system inside a stealth fighter without compromising the stealth, the speed, or the combat capability? The answer required the Skunk Works to build what is essentially a hidden second engine inside the airframe. Here's where things get interesting. Remember the F-135 engine, the most powerful fighter engine ever built, 43,000 pounds of thrust? In the F-35B variant, designated the F-135 PW600, that engine doesn't just push the jet forward. It does something no other fighter engine on Earth can do. It splits its power in 3 directions simultaneously. At the rear of the aircraft, you see the Three-Bearing Swivel Module, called the 3BSM. This is the exhaust nozzle, built on 3 mechanical bearings that allow the entire assembly to rotate 95 degrees downward in just 2.5 seconds. When the pilot initiates the transition to vertical flight, the 3BSM swivels from pointing straight back to pointing almost straight down, redirecting 18,000 pounds of hot thrust toward the ground. And it uses fuel pressurized to 3,500 psi as hydraulic fluid to power the rotation. Not hydraulic oil, jet fuel. They call it a fuel-hydraulic system, and it saves hundreds of pounds of weight. But the problem is that 18,000 pounds of thrust at the back of the aircraft would just flip the nose straight into the deck. You need something pushing down at the front too, and this is where the engineering gets genuinely brilliant. Behind the cockpit, hidden under these doors that open on both the top and bottom of the fuselage, sits the Rolls-Royce LiftFan. This is the hidden second engine, except it's not really an engine at all. Picture a 50-inch diameter turbofan. Now remove the combustion chamber, remove the fuel system, and what you're left with is a purely mechanical fan. 2 stages of counter-rotating titanium fan blades, manufactured using superplastic forming and linear friction welding, spinning at enormous speed. What drives it? A driveshaft running forward from the main engine, connected through a dry carbon-carbon clutch, the same technology used in aircraft brake systems, and a beveled gearbox that turns the power 90 degrees upward into the fan. About 1/3 of the engine's total power is redirected forward through this shaft to spin the lift fan. When the pilot presses the transition button, the clutch engages at low engine speed, locks mechanically, and then the engine spools up, transferring roughly 29,000 horsepower through that shaft. For perspective, that's the output of about 29 Formula One engines, channeled through a single drive shaft running through the aircraft's fuselage. And if that clutch doesn't engage cleanly, or if the shaft fails under load, the math is simple and terrifying. 25 tons of aircraft, 200 feet above the deck, with no way to maintain hover. There's no second chance. The gearbox is so robust it can operate for up to a full minute with uninterrupted oil supply while still transferring full power. All of that energy spins the lift fan, producing more than 20,000 pounds of cold, unheated thrust straight down through the belly of the aircraft. There's an elegance to this design that's easy to miss. The lift fan produces what engineers call cold thrust, just moving air, no combustion. The 3BSM at the rear produces hot thrust, superheated exhaust. Cold fan at the front, hot nozzle at the back. They balance each other, and the combined effect is a 50% increase in total vertical thrust with virtually no increase in fuel consumption. Compare that to an afterburner, which gives you 52% more thrust, but drinks fuel at a catastrophic rate. The shaft-driven lift fan concept is, pound for pound, one of the most efficient thrust augmentation systems ever devised. It won the Collier Trophy in 2001, the highest honor in American aeronautics. An idea from the 1980s, dismissed as impossible for nearly a decade, had become the most efficient thrust augmentation system ever flown. Sometimes engineering isn't about being right first, it's about being right eventually. 2 small nozzles called roll posts sit inside the wings, one on each side, bleeding bypass air from the engine to produce a combined 3,900 pounds of downward thrust. That handles roll control. Together, the 3 systems produce roughly 41,900 pounds of total vertical lift across 3 balance points: front, back, and sides. It's like balancing a dinner plate on 3 fingers. Move any finger and the plate tilts. The flight computer adjusts all 3 thrust sources thousands of times per second. The jet approaches from the stern, decelerating. The 3BSM swivels. The lift fan doors open, 29,000 horsepower transferred through a carbon clutch to a hidden turbofan with no combustion. Roll posts stabilize the wings, 3 thrust points, balanced by a computer thousands of times per second. The aircraft slows to a hover, 25 tons of stealth fighters suspended in air by nothing but directed thrust. The deck below is pitching in ocean swells. Crew members stand 30 feet away. The deck coating is rated to withstand 1,000-degree exhaust because standard non-skids simply would melt. And here's what the pilot actually experiences. Every conventional flight control surface, ailerons, rudder, elevators, become useless in a hover. They work by redirecting airflow over moving surfaces. In a hover, there's no airflow. You're just sitting in the sky. So the flight computer takes over entirely. Pitch control, nose up or down, comes from varying the thrust split between the LiftFan at the front and the 3BSM at the rear. Yaw control, turning left or right, comes from swiveling the 3BSM side to side. Roll control comes from the wing roll post. Forward or backward movement comes from tilting the 3BSM and adjusting variable vanes in the LiftFan's exhaust. The pilot flies it with the same stick and throttle as conventional flight. Push forward, the jet moves forward. Pull back, it moves back. Tilt left, it slides left. The computer translates those familiar inputs into thrust vectoring commands across all 3 systems simultaneously. The pilot doesn't think about which nozzle to move. They don't manage individual thrust percentages. They just fly. The computer handles the impossible math. Harrier pilots used to manually manage nozzle angles while simultaneously flying the aircraft, a workload so intense it contributed to one of the highest accident rates in military aviation. The F-35B eliminated that entirely. This entire system, the LiftFan, shaft, clutch, gearbox, roll posts, adds roughly 3,000 pounds compared to the conventional F-35A. That's the weight penalty for being able to land on a ship with no runway. And every single one of those 3,000 pounds had to come from somewhere else. The airframe is 35% composite materials by weight. Bismuleamide, composite epoxy, carbon nanotube reinforced structures in later production lots. Every structural decision was a trade-off between strength, stealth, and weight budget that vertical flight demands. Engineers at Lockheed spent years shaving ounces from every system to make room for the STOVL components. The result is an aircraft that can do everything the F-35A can do. Fly at the same speed, carry the same weapons, maintain the same stealth, and also land vertically on a moving ship in the middle of the ocean. But pure vertical landings have a cost. The aircraft burns fuel hovering, which means pilots sometimes have to dump unused weapons and fuel into the ocean before landing. Exactly what Harrier pilots did for decades. Engineers needed a way to land heavier. The answer called shipborne rolling vertical landing. Instead of a pure vertical descent, the pilot brings the F-35B in with some forward speed, maybe 40 or 50 knots, using a combination of vertical thrust and wing lift to touch down in a short roll. Disc brakes bring it to a stop, no tailhook needed. The aircraft lands heavier this way, carrying more unused weapons and fuel back to the ship instead of dumping them in the ocean, which is exactly what Harrier pilots had to do. British test pilot Peter Wilson performed the first SRVL with an F-35 on October 13, 2018, landing on HMS Queen Elizabeth. It's like the difference between parallel parking and pulling into a spot. Same result, but one lets you bring in more groceries. Then it descends, straight down, landing gear touching steel with the precision of an elevator. The United States now operates 9 amphibious assault ships, America-class and Wasp-class vehicles that deploy the F-35Bs. That nearly doubles the number of ships in the fleet capable of launching stealth fighters. 9 additional floating air bases, each carrying a squadron of 5th-generation combat aircraft. And the F-35B doesn't even need a ship. It can operate from damaged runways, highways, any 600 feet of flat surface. In a conflict in the Western Pacific, the scenario the Pentagon plans around the most, enemy missiles would likely crater conventional runways in the first hours. Every aircraft that needs 8,000 feet of concrete is grounded. The F-35B keeps flying. That's what this aircraft was built to do. Take off from a ship that has no business launching stealth fighters, fly invisible, see everything, and come back to a moving deck in the middle of the ocean by hovering like a helicopter. A yellow shirt on deck watches it land. Just another Tuesday. Bye for now.